Welcome everyone to the next set of the DIMAP seminar talks. So our first speaker of this term is Bernstein from Rutgers. So Aaron did his PhD from Columbia under Cliff Stein, and after a postdoc at the TU Berlin with Martin Scutella, he's now at Rutgers. So he's made several important contributions to dynamic graph algorithms and streaming algorithms with several best paper awards at top conferences. And so today he is kindly agreed to tell us about some exciting recent work on min cost flow and dynamic shortest paths. So Aaron, a virtual welcome to Warwick. And
Thank you.
Whenever you're ready, over to you.
Okay, thanks so much. So, hi everyone. So today I'm going to talk about two results that are somewhat related. So the first one is on dynamic shortest paths. So let me quickly introduce the problem. So we're going to be looking at single source shortest paths. So here, basically, you have some fixed source, and you want to compute distances from the source to every vertex in the graph. So if you have a fixed graph, you can use any sort of classic algorithm like BFS or Dijkstra and solve this in around linear time. But we're going to be looking at the dynamic setting, where you want to maintain information in a graph that's changing over time. And the standard model here is what's called fully dynamic. So basically, the adversary has a sequence of update and query operations. And an update operation changes the graph, and it changes one edge. Whereas the query operation, you then have to return a shortest distance or shortest path in the current graph. And the goal generally is you want low query time. When the user actually asks for a distance or path, you want to return that quickly. And then you want to minimize the update time as much as you can. So let's think about the trivial algorithm for this problem. Whenever an edge changes, you could just recompute shortest paths from scratch from the source using your linear time algorithm. So this would be order m update time. But we would like to do better because you're only changing one edge at a time. You shouldn't have to recompute things from scratch. Unfortunately, for this most general case, there are conditional lower bounds showing actually you can't do better, even if you allow 1 plus epsilon approximation. So to try to make progress, people have relaxed the model. And I think by far the most common model that people use for this problem now is the decremental setting. So here, the adversary is restricted in their updates. They can only delete edges or increase edge weights. They can't insert new edges. So in particular, because of this, distances in the graph are monotonically increasing. And there are several motivations for this model. One is just that it's a natural relaxation of the fully dynamic one, and we need a relaxation if we're going to hope for non-trivial results. Another is that this is actually often used as a subroutine in many other problems related to shortest paths, like all pair shortest paths or diameter, these sorts of problems. And finally, as we'll see, this can be a very powerful data structure in static algorithms. Okay, so what's known for this problem? So let's assume for simplicity that just for this talk that the graph is unweighted. So basically the decremental setting means you start with some big graph and the adversary just deletes one edge at a time until you have an empty graph. And you have to maintain shortest paths throughout that whole sequence. So the trivial algorithm again would be every time the adversary deletes an edge, you just recompute shortest paths from the source from scratch in linear time. So now the total number of updates is like order m, because each update corresponds to an edge deletion. So over all deletions, this would be like m squared time. And there's a classic algorithm from 1981 which improves upon this and gets mn total update time, and a conditional lower bound showing that this is optimal. So in order to break through this mn, recent work has allowed a 1 plus epsilon approximation, because here 1 plus epsilon really will help you break through the lower bound. All right, so I'm about to tell you sort of what's known then with a 1 plus epsilon approximation. But first, I need to distinguish between two kinds of dynamic algorithms. So there are basically two models when you talk about dynamic graph algorithms: the stronger model and the weaker model. The stronger model is what's called an adaptive adversary. So this is really what you would naturally think of, where the adversary is just allowed to give you any sequence of update and query operations. And in particular, they can do things like query a path and then look at the path you return and delete every edge on the very path you returned. So they're adaptive because the updates can actually depend on the query path that you return. And note that any deterministic algorithm is always going to work against an adaptive adversary, because if the algorithm is deterministic, the adversary knows everything your algorithm is going to do. But there's a weaker model called non-adaptive adversaries, also sometimes called oblivious adversaries, where the adversary can't respond to what your algorithm does. They have to fix the entire sequence of updates and queries in advance. The algorithm doesn't know what they fixed, but the adversary does have to fix everything in advance. And many randomized algorithms only work against a non-adaptive adversary, because basically many randomized algorithms assume that the adversary has zero information about your random choices. And an adaptive adversary can figure out the random choices by looking at the queries, and we'll see examples of that. But a non-adaptive algorithm has zero information about random choices. So that's where the model becomes very different. Right, so to summarize, we have a stronger model, which we just assume it knows all random choices, and a weaker model that has zero information about random choices. And basically, non-adaptive algorithms turn out to be much easier to design because they can use randomness to hide information from the adversary. They have this additional power. So they're much easier to design, but for that very reason, they also have significant limitations. It's a significantly weaker model. And I want to talk about two limitations. So the first is kind of in terms of practical applications. If you imagine an application like Google Maps, and you ask it for a route, it gives you a route. But as if many users, if it returns the same route for many users, then the traffic on that route will go up. And it'll basically have to increase the edge weights on that path because no one will want to use that route anymore. So it's effectively increasing the weight on the edges of the very path that it returned. So this is an adaptive setting. And you would have to use an adaptive algorithm here. The second limitation is a more kind of purely theory one, which is that, as we'll see, we often want to use a dynamic data structure as a kind of subroutine in a larger algorithm. But only non-adaptive, only adaptive algorithms can be used as black box data structures. A non-adaptive algorithm can't be used as black box because it can only handle particular sequences of updates and queries that are all fixed in advance. Okay, so these are kind of the main reasons we might want an adaptive algorithm. And in general, because non-adaptive algorithms, as I said, were often much easier to design, there's this big gap in dynamic algorithms for many, many problems between the best adaptive and best non-adaptive algorithm. And closing that gap has been a really big focus of the field for the past decade. Okay, so what's known for this problem? So we want to maintain distances from a source. And we said there's this mn time algorithm, total update time over all deletions for the exact version of the problem. So if you allow approximation and you assume a non-adaptive adversary, you can actually solve the problem in linear time. And this is, by the way, like there's a lot of work leading up to this. So just to keep things simple, I'm skipping all the prior work. I'm just showing the state of the art. So this is like a big breakthrough. And in particular, note that this is basically optimal because order m is how long you need just to compute a shortest path in a fixed graph. And this algorithm in basically the same running time is actually maintaining a shortest path throughout the whole sequence of deletions. Okay, so for non-adaptive algorithms, the problem is basically settled. But for adaptive algorithms, it seems much harder. And there's been a lot of attempts to do this, but you can see we're still quite far from linear time. Okay, so what is our result? Well, again, we have this gap, and we basically close the gap. So we show that there's an adaptive algorithm which gets this near linear update time. So this closes the gap. Again, it's optimal up to subpolynomial factors. It can generalize in all the ways you want it to generalize. And so this essentially settles the whole problem now, because we have a near linear time algorithm in the strongest model. Okay, so that's result one. Result two is on totally unrelated problem. So it's about flow problems. So I'm not going to go into like the details of flow algorithms. Most of this talk is going to be about shortest paths. So I'm not really going to define them really carefully. I think we all basically know what a flow problem is. You have a source, you have a sink, you have some capacities, you want to send flow. So kind of just a brief definition, we're going to have an undirected graph. You have a fixed source and sink, and you have some capacity function, and you want to find a flow that obeys the capacity function. All right, so this is a classic problem, and it's covered in like most undergraduate algorithms classes. It's been around for many, many decades. One of the reasons it's been around for so long is because this problem captures many different kind of things you might want to capture. And in terms of applications, the obvious application would be something like water flowing through pipes, but you could also use it to, for example, model like the flow of money through a financial system. So there are all sorts of different applications to this problem. Okay, so what's known? So there are many variants that you might care about for this problem. So the standard variant is the one I showed you. So edge capacitated max flow. So every edge has some capacity. You want a flow which satisfies these capacities. But here's some very common variants. One is vertex capacitated max flow. So now every vertex has a capacity, and your goal is to compute a flow such that the flow going through any vertex, the total flow going through any vertex, is at most the capacity of that vertex. And finally, you can ask about costs. So each edge now has a capacity, but also a cost. And you have some cost budget, some total budget. And you want to compute a maximum flow whose total cost is less than this cost budget. And again, the details of these definitions won't really end up mattering. Okay, so what is known? Well, so exact max flow, it's been around for many decades. There are probably dozens of results. So I'm really skipping like all the prior work, and I'm just showing you this extremely recent breakthrough that gets m plus n to the 1.5. And for unit capacities, there's also this other recent algorithm. So the nice thing about both of these algorithms is they both extend to all the variants, like min cost flow and vertex capacities. So for the exact case, we're sort of slowly getting better and better, but we're still quite far from linear time. So for this reason, people have also turned to a relaxed problem, which is what happens if you allow approximation and you assume an undirected graph. And here there is this sort of breakthrough results which show that actually you can just do near linear time here. The issue is that these algorithms don't extend to any of the variants. In fact, if you want to extend them, they only extend to a very special case called transshipment, where you have costs, but you don't have capacities. And there's this isn't just a matter of like, oh, well, you need to just like tweak the algorithms to get them to work for these different cases. There are fundamental reasons why they don't seem to extend, because these algorithms use something called oblivious routing. They're a reduction to oblivious routing. And basically, oblivious routing, for example, you can't really get a good oblivious routing for vertex congestion. There are lower bounds showing that's not possible. So it seems you would need to do something fundamentally different or fundamentally change this technique in some way. Great. So just to summarize, for exact max flow, we have this m plus n to the 1.5. For approximate, we can do m for the most basic version, but for all the extensions, we just have to run the exact case. There is no good approximate algorithm. And so an open problem that's sort of been around for a while is, can we solve approximate min cost flow or vertex capacitated flow in linear time? And our result is yes. So we show basically how to get near linear time for all of these different variants. And so this essentially completes the picture for approximate flow in undirected graphs. Okay, so those are two results. So you might ask, why are these related? Like, why are these part of one talk? Dynamic shortest paths, max flow. What do these have to do with each other? So I will briefly address that. So there's something called the MWU framework for solving maximum flow. So now, I'm getting to slightly more technical stuff. This is still pretty high level, but it's going to get more technical. I should say, definitely feel free to ask questions if there are any questions. I can dwell on things. Okay, so the MWU framework is as follows. So you're given a source and a sink. So you want to solve flow. And what you do is you're actually going to introduce a weight on every edge. This is in an internal weight used by the algorithm. And it starts with some simple initial weight function. And then what the algorithm does at a very high level is that it computes an approximate shortest path given your weight function from S to T and then it sends flow on that path, and then it increases the weights of all the edges on that path, and then it repeats. Okay, so this is, I was gonna like draw something here, but there are technical issues. For some reason, I can't annotate on Zoom right now. So I won't draw a figure for this. For the really important figures, I will sort of switch to a whiteboard and draw them there. This is not a very important figure. I was just gonna draw a single path. So I apologize, some of the figures will be missing. So basically, the high level intuition here is, imagine you compute some path from S to T. Well, and you send some flow on it. And now you want to compute another path. You want to send flow on another path. Well, intuitively, the goal of flow is to spread out the flow as much as possible because you don't want to overload the capacity of any single edge. So when you compute that second path, you want to discourage the algorithm from using any of the edges on your first path because you don't want them to be overloaded. And that's exactly what this is doing. So basically, by increasing the edges, by increasing the weight on any edge that you use, you're sort of discouraging the algorithm from using that edge in the future. So it's always, the algorithm tends to pick paths that haven't received much flow yet. That is the high level intuition. So this is a quite old framework, and there's a very slick primal dual analysis by Garg and Kuhneman showing that if you run this algorithm, you actually end up with a 1 plus epsilon approximation to max flow. And this very easily generalizes to all the variants like min cost flow and vertex capacities. All right, so the question though is, how do we actually get this framework to run efficiently? Well, so recall, we have this framework, which is that you just repeatedly compute a shortest path from S to T. And note that, the first bottleneck we see is just we have to compute many, many shortest paths in step 3. This is really gonna last for many iterations. So, and moreover, the shortest path is in a different graph each time, because after every shortest path you compute, you're changing some edge weights. So your shortest path changes every time. So the original algorithm for this problem actually just computed the shortest path from scratch in every iteration. But it was observed by Madri in 2010 that, wait, you can speed this up with a dynamic algorithm. I mean, you're just repeatedly computing shortest paths in a graph where weights are increasing. So this is decremental single source shortest paths. Decremental because weights are only increasing. And in particular, if you have a good data structure, then the total running time to compute all these paths will just be the total update time of your data structure. All right, so let's say we want to run MWU in near linear time. There are actually 2 challenges that you face. And the first is that, as I said, you need a good data structure. You need a data structure with total update time order M, and you need it to be adaptive, right? Because what the MWU algorithm does is it asks for a path, and then it increases all the edge weights on precisely that path. So there's clearly a very tight relationship between updates and queries. You need an adaptive algorithm. All right, so this was precisely our first result. And our min cost flow result just uses our SSSP data structure as a black box. Unfortunately, this doesn't quite settle the problem. There's a second challenge, which is that even if your data structure can find the paths really quickly, at the end of the day, MWU has to go through every path that you find and one by one update the weights on all the edges. So the running time is at least going to be the total length of all the paths that you return. And it turns out this total length can be too long. This is what's known as the flow decomposition barrier. So I will talk about it for a little bit. So here's a question. So say you're given some flow and you try to, in some optimal way, kind of decompose that flow into paths so as to minimize the total length of the paths. Then can you upper bound the total length of the paths that you're going to end up with? So if you have unit capacity edges, it's easy to show that the total length of the paths is order M because every edge gets used at most once. But in general capacity graphs, that's not the case. And again, I unfortunately can't annotate, but basically you can see that the optimal flow will basically take n different paths from S to T, each using one of these parallel paths. And so each path has length n, because each path has to share that blue tail at the end, but the number of paths is also n, and all these paths have 1 unit of flow on them. So the total length of your paths is actually n squared, even though the number of edges in the graph is only n. And so more generally, more generally, you can show that for general edge capacities, the total length of the path can be as big as Mn, and for vertex capacities, it can be as big as n squared. So this is what's known as the flow decomposition barrier. And the point is that all previous MW algorithms were not able to get past this flow decomposition barrier, because as long as you're really sending flow down every path that you find and sort of adjusting the flow on each edge, you're always going to be stuck at this barrier. You're not going to be able to beat those times above. So to go back, we have these two challenges. The first is that we need a good data structure. And the second is we need to break through this flow decomposition barrier. And we do that by significantly changing the MW framework itself and introducing randomization in various ways. So basically, our min-cost flow result introduces the first solution to both of these above challenges. And I should note that these solutions have nothing to do with each other. The only reason that these two things are part of the same talk is because we need both of them for min-cost flow. They're really totally unrelated. The first one is about dynamic shortest paths. The second one is about MWU. They have no relation. So for this talk, I'm going to focus only on the first challenge. I think that was the more significant challenge. I mean, this was sort of a long-standing open problem in and of itself, and it was definitely sort of technically by far the more challenging one to solve. So I'm going to focus on decremental shortest paths for the rest of this talk. Okay, so I want to introduce our key building block in order to do this. So let's start with just quickly reviewing the model. You have a source S. You assume the graph is unweighted. So each update just deletes an edge in the graph. And your goal is to maintain approximate shortest paths or distances from S. And we want our algorithm to be adaptive. So we're going to show how to do this in near linear time. So, okay, in order to solve this problem, basically all modern algorithms for this problem use the same approach, which is that they start by decomposing the graph into low diameter balls. It might not seem intuitive why this is the case. I mean, I haven't even drawn a source on this graph. It's really like it has nothing to do with the source. You just try to decompose the graph into low diameter balls. Intuitively, you're then somehow able to compute information within each ball. And then somehow, once you have a lot of information within each ball, you can sort of compress the balls and you end up with a compressed graph. And then you can kind of recurse. You can compute more balls and compress those. And in the end, you end up with a much easier graph to work with. For those of you who have seen a bit on this before, basically inside a low diameter ball, you compute shortcuts and then you get a hop set and so on and so forth. I'm really not going into the details. You'll just have to trust me that basically, although it doesn't seem that related, really like every fast algorithm for this problem uses this decomposition into low diameter balls. So in general, as a static problem, this is pretty easy to do. As a dynamic problem, this is quite hard to do. And in particular, there's a key building block that you're going to need if you're going to do this, which is that let's say you start with one of these green balls. And again, I apologize, I can't draw here. But basically, if you start with some ball that initially has low diameter, after the adversary deletes some edges, some of the vertices in that ball, the ball might no longer have small diameter after some deletions. Some of the vertices might be far from the rest of the ball. And so you have to detect that and you have to say, okay, this is no longer a low diameter ball because these vertices are far from the rest of the ball. So basically that's a subroutine that you're going to need if you're going to use this basic approach. And so one of the things we did is we sort of tried to just abstract away that subroutine and say, okay, let's sort of define it formally and see how we can solve it. All right, so I'm about to define the subroutine. Let's just start with basic definitions. So again, these hats and tildes over the O and omega, you can ignore those. They're just hiding small factors. We're assuming G is unweighted. And finally, we have this standard definition of weak diameter. Okay, so here is the this abstraction that we define for maintaining a low diameter set. So we call this robust core because basically the low diameter ball is a core. We want it to be robust in the sense that you can sort of, as deletions come, you can always maintain some low diameter set inside that. So the input is a graph subject to edge deletions, and you assume that graph has small diameter. And so the goal is to maintain a set K inside the graph such that K has low diameter, right? So initially you just set K equals to the vertex set because the whole graph has low diameter. But as you delete edges, the graph might not have low diameter, and so you need to maintain this low diameter set K. So I'm trying to think about how to do this. Okay, I'm gonna share a whiteboard, I think. That's the only thing I seem to be able to annotate on. I again apologize for the technical difficulties. So, oh, hey, amazing. It seems to show both. That's fantastic. Okay. Great. So then I can sort of have this down here. Okay, this makes my life much better. Oh no, you can still only see one. Okay, sorry, it's not as good as I had hoped. Okay, so then let me just draw for this. So you have your graph G. And initially, this graph has low diameter, but over time, some parts of the graph might sort of become far from the rest. And so you want to maintain the set K inside G that has low diameter. But let's sort of be a little more formal, right? The question is, how do you know that you can throw a vertex out? How do we know that these red vertices can be thrown out? So let me actually draw this more carefully. So you have a graph G. This is your beginning graph. It has small diameter. And now you can imagine that after some number of deletions, you end up with a graph that looks something like this. Okay, so what vertices would you say still are in your low diameter set and what vertices are not? Well, if you look at this vertex here, then the thing to note is that the ball around this vertex of diameter, let's say 2D, is mostly so basically this ball contains most of the graph. So in particular, if you look in the original graph, if you look at any vertex, then actually the ball around that vertex of just radius D is automatically in the graph because the graph is diameter D. So originally, sort of, if you look at a ball around any vertex, it touches the whole graph. In this changed graph, the ball around V might not touch the whole graph, right? It might sort of end here, but it touches most of the graph. And so this vertex clearly still belongs in your low diameter set. On the other hand, if you look at this vertex here, then its ball of radius 2D might only reach this far. So this ball is far from most of the graph. And so you can throw it away. You can say, okay, this vertex has to go. It's no longer part of my set. All right, so going back to the slides. What I just said corresponds to the scattering property. So you want to set K that has low diameter, and you want it to have the scattering property, which says that basically, if I throw a vertex out of the graph, it's only because the ball around that vertex has lost access to some fraction of the graph. Okay, so this is the problem we want to solve. And then there's a termination condition, which isn't very important, which is just that if the set you're maintaining ever becomes quite small, like less than half the graph, then you could just say that, okay, my low diameter set has fallen apart. The thing I'm maintaining is less than half the graph, so it's basically fallen apart, and you can just terminate the whole thing. Okay, so then our algorithm basically has two parts. And the first is solving this robust core problem, this building block of maintaining a low diameter set. And that's going to be the whole focus of this talk. And then the second part is showing that once you solve it, you can actually solve decremental SSSP. And there's a lot of additional work that has to go in here, and we sort of need new techniques, and we also borrow a lot from the existing literature on dynamic shortest paths. But this second part is basically like enmeshed into all the existing techniques and modifying them in the right ways. Whereas the first part is kind of where I think the main new ideas are coming in. So that's why I'm really just focusing on this robust core problem. Okay, so let me briefly talk about previous approaches to this problem. So again, this is how we define the robust core problem. And the key thing I want to say is this is not just a problem that we need. It's not just a subroutine particular to our algorithm. As I was trying to point out, basically all the existing algorithms, because they need to maintain low diameter sets, they all need to use something like this. They don't all define it this way. In fact, many of them have to solve a significantly stronger, harder problem that gives more information. So we kind of tried to distill the most basic version of the problem that all these different algorithms have to solve, and that's what robust core is. And this building block, I think, was sort of the main obstacle to progress on this problem. So let me talk about what was previously known. Okay. So first I want to talk about what if your algorithm is allowed to be non-adaptive? In that case, it turns out that the robust core problem is actually pretty easy. So here's another case where I really wish I could draw. So give me 1 second. I wonder, this will probably not work, but I want to try something. No, it's still, I can't seem to share both files at once, unfortunately. Okay, I think maybe this is better to just draw as a picture then. So here's the algorithm. You have your graph G. And what we're going to do is we're going to pick a random source S. And it's very important that it's random. And we're going to maintain a ball around. So what the algorithm does is it picks this random source S and it maintains a ball around S up to radius 5d. So originally, this ball will just contain all of G, right? Because G has diameter d. Maybe I'll even make that clear. So diam of G is equal to d. So you have this ball up to radius 5d, but as edges are deleted, this ball might no longer cover the whole graph. And I should say that maintaining this ball can be done efficiently because you're just maintaining a ball from one source up to a small distance. You can just use like evidential Loach. There's a standard algorithm to do this. So you maintain this ball around S. And what you do is any vertex that leaves this ball, you throw out of your core. So basically, this green part is going to be K. And anything that leaves this green part is going to be thrown out of K. So now we have to be careful here, though, because we want to make sure that we satisfy this scattering property, right? So the scattering property said that if we're going to kick this blue vertex V out, it has to be because V is now far from a bunch of the graph. So how do we show that that's actually the case? Well, let's also consider the ball of radius 2d around S. So note that that ball is disjoint from the ball of radius 2d around V. So basically, if we look at the ball around V, we know that it definitely can't reach this red ball around S. So as long as that red ball is big, that tells us that V can't reach a big chunk of the graph. But if that red ball ever becomes too small, then we're no longer going to be able to say that. We can no longer guarantee that just because V is far from that red ball, it's far from the rest of the graph. Maybe it's only far from that tiny red ball and nothing else. So basically, this algorithm, we can only persist with this source as long as as long as this ball around S is big. And if the ball ever becomes small, we're going to pick a new source because this is no longer a good source. So we're going to restart with a new source. All right, so now I'm going to go back to my slides. So that's exactly what we have here, right? We maintain this ball around S, that's the big ball. And whenever a vertex leaves that big ball, we're going to remove it from our core. But we can only do this as long as this smaller red ball around S remains big. If it ever becomes small, we just have to restart with a totally new source. So let's think about the analysis. So picking one source is easy. As long as you have one source, you can do it in like linear time. So really the whole analysis is about showing that you're not going to need to have too many sources. And the argument is as follows, that when do we terminate a source? Well, we terminate it when the ball around that source has become small. But that means that the source has now become scattered, meaning we should throw the source out of the core. If the ball around that source is small, that means that source is far from much of the graph, so we can throw it away. And now here's the key thing. We picked our source at random. So if the source became scattered, if it became far from much of the graph, then in expectation, half of the vertices in the graph must have become scattered, because the adversary has no idea what the source is. So if it wants to scatter the source in expectation, it has to scatter about half the vertices in the graph. So with high probability, after log n sources, you scatter half the vertices each time, and everything will be scattered, and you can terminate. All right, so I showed this algorithm. This is not our algorithm. This is a non-adaptive algorithm, but to kind of highlight why things are so much easier in a non-adaptive setting. This random source technique is really powerful, but it's totally useless in an adaptive setting. Because the key argument of the non-adaptive setting was that the adversary doesn't know the source, and so to scatter the source, it has to scatter half the vertices in the graph. But in an adaptive setting, you can show that the adversary can easily guess your source by looking at your shortest path queries. And if the adversary knows the source, then all it has to do is just delete only the edges incident to the source. And then you pick a new source, and then it deletes only the edges incident to that source. And so basically, you can end up with n sources. So this will be very inefficient. And this one technique, although it seems really simple, it really highlights the power of non-adaptive algorithms, which is that you can pick this random vertex that the adversary doesn't know, so you can hide information. And in fact, like this one tech source is used a lot, and it accounts for much of the gap between adaptive and non-adaptive algorithms. So we need something new here. So what have previous adaptive algorithms tried to do? Well, to kind of highlight how much harder the adaptive setting is, because they couldn't pick a random source, they actually end up just maintaining a shortest path tree from every source. That's the best we know how to do. And then you can sort of use density arguments to try to limit how much these shortest path trees from the different sources intersect. And so you have these running times which are better than MN, but they're still far from linear. And both of these papers also make clear that there's a hard barrier to this approach. You can't do better than M root n with this approach. So we're going to need something very new to get linear time. Okay, so now I'm going to start talking about our approach to the problem. So our approach is based on expanders. Let me quickly just describe an expander in picture. So and basically, if you have a graph G and you look at any cut in the graph, an expander basically says that if you look at the neighborhood of this cut, meaning, so this is going to be a vertex expander, by the way, and that's going to be clear from the slides. So I'm going to look at the neighbors of the vertices in L. And here I'm defining this neighborhood N of L to be disjoint from L. So it's the neighbors that aren't in L. And basically, it's an expander if N of L is large with respect to L. So it should be like L over log N. So that's what an expander means. It means if you take any set and you look at its neighborhood, the neighborhood is big with respect to that set. So an example of something that's not an expander is if you had a graph that looks like this. This is not an expander, because if you set this left thing to be L, the neighborhood of L is very small, so it's not an expander. Okay, back to my slides. So we can see that definition here, that N of L is the neighborhood of L, and it's a vertex expander if for any set L, the neighborhood is big with respect to the set. And so for this talk, always vertex expanders, always this expansion factor of 1 over log N. So why do we care about expanders? Well, expanders have two key properties. One is that it's easy to show that if you have an expander, it has small diameter. The second key property is that expanders are robust to edge deletions. So in particular, in expanders, you can do this thing called expander pruning. And I'll draw a figure of this in a second. But basically what expander pruning says is that if you have some original expander and the adversary starts deleting edges, then most of the edge deletions won't have a big impact on your expander. So basically, maybe they can disconnect some small parts of the expander, but because the expander is so well connected, if you only delete a small number of edges, this will only have a small impact. So you can always maintain a large set that remains an expander in the original graph. And basically, as long as the number of deletions is not too big, like n over log n, you'll always have this large expander inside G. So just to sort of quickly draw this is not a very complicated figure. Basically, all this is saying is if you have a graph G, then if you delete some edges, this might sort of cause some part of the graph to no longer be expansive. But as long as the number of deletions isn't too big, you're always going to be able to maintain a set X inside, which is still an expander. Okay, so expanders have these two great properties. They have small diameter and they're robust to edge deletions. So to show that these are so useful, let's start with an idealized scenario. Let's say that in robust core, your original graph, it's not just small diameter, it's actually an expander to begin with. And I want to show how to solve the problem in this idealized scenario. And the algorithm is actually exactly the random source algorithm you'll see. It's just instead of a random source, you pick an expander. So let me show how this works. So initially, your low diameter set K is just the whole graph. And now you're going to maintain this expander inside the graph. And you're going to maintain a ball around that expander of radius 2d. And you're going to remove a vertex from your core whenever it leaves that ball. So I think another figure is in order. I apologize for having to jump around so much. So we have our graph G, which again initially has low diameter. And the point is that as edges are deleted, we can always maintain the set X inside of G. So, and now we're going to maintain a ball of radius 2d around X. And so this green set, this is going to be, oh, sorry, that misdrew a bit, but this is going to be the set K. That whole green set. So in particular, we're throwing away all of the vertices in here. Sorry, there's also lag on my thing. So now we need to argue that, like before, you can throw away these vertices in the outer edge. And the reason is that, note that this vertex V is definitely far from X. It's at distance more than 2d from X. So as large as that red set X is large, then we could say that any vertex that's far from X can safely be thrown out. So we satisfy the scattering property. We also satisfy the diameter property. We know this green set has small diameter because X is an expander, so X has small diameter, and then we just go up to distance 2d past that, so the ball still has small diameter. So we can keep doing this as long as X is large. But if X becomes small, then again, then the argument no longer works. So let's go back to the slides. So that's exactly what our algorithm was, but we have to terminate once X becomes small. So here, I'm not saying what to do once X becomes small. The algorithm just stops working. This is just to give an intuition of why expanders are good. But the key thing is that, yes, X can eventually become small, but this can only happen after a lot of deletions. That's what pruning told us. Because G is originally an expander, this problem is only going to occur after a lot of deletions. So basically, this is an algorithm that's going to work for quite a lot of edge deletions. And note, again, this is exactly like the random source algorithm, except we're rooting at an expander instead of a random source. And the intuition is basically, in the non-adaptive setting, if you pick a single random vertex, that's actually a robust thing because the adversary doesn't know the random vertex. In the adaptive setting, picking any one vertex is never going to be robust, but picking an expander as your source will be robust. Okay. So, of course, the question is, what if your original graph is not an expander? Right? The input to a robust core just guarantees that the core has small diameter. It doesn't guarantee anything about it being an expander. And I want to note that sort of, if you've seen this kind of work before, then probably the first thing that comes to mind is, well, if I have an algorithm that works for expanders and I want an algorithm that works for general graphs, I'll just do an expander decomposition. But for various reasons I can talk about if you ask after, it's very unclear how to use expander decomposition for this problem. So the kind of cool thing about our result is we don't need to decompose the graph into expanders. We're actually able to use expander tools without ever decomposing into expanders. We're actually able to use expander tools on a graph that doesn't originally look like an expander, but we basically show how to turn it into an expander. Okay, so now we can sort of talk about the main tool that we use. So what if G is not an expander? Well, given any graph, I want to define this notion of criticality of vertices. Basically, a vertex is critical. You can think of it as a vertex is critical if deleting all the edges around that vertex significantly decomposes the graph, scatters a lot of vertices. So for example, in the, and again, sorry, I can't draw here. So number 1 corresponds to this top right. So that graph is an expander. So there, none of the vertices are critical. If you remove any one vertex in that graph, all the other vertices are still going to be very connected. So number 2 corresponds to the bottom graph. And you can see there that a lot of the vertices are critical. All the edges in the middle of, all the vertices in the middle of the path, if you remove any of those vertices, you'd like break the graph up into 2 big pieces. So those are all extremely critical vertices. So basically, in an expander, no vertices are critical. In an arbitrary graph, you can have lots of very critical vertices. And the main claim we're going to show is that, well, what if G is an arbitrary small diameter graph? Now, this graph, that's the top left. You can see that's definitely not an expander because that middle edge is like, those 2 middle vertices are extremely critical. But most of the vertices are not critical. It's just the 2 middle vertices and the ones next to them that are critical. If you kind of delete other vertices, like other random vertices, it really won't have any impact. And so what we're going to show is that in a small diameter graph, yes, some vertices can be very critical, but the total criticality is small. Most of your vertices don't really matter. Okay, so to this end, we define what's called a capacitated expander. So a regular expander, we said, is if you take any set, then its neighborhood is big with respect to that set. In a capacitated expander, we're going to define, I don't know what happened there. No, 1 second. In a capacitated expander, we're going to define a criticality kappa for each vertex, which I also call the capacity of that vertex. So now basically, the graph is expansive if given any set L. If you look at its neighborhood, you don't need the number of vertices in the neighborhood to be large. You just need their total capacity to be large. So if you have few vertices in the neighborhood, but they all have really high capacity, this would still count as a capacitated expander. So now the definition of expansion is with respect to this capacity function kappa. So let's go ahead and see some examples. So again, this is the definition. So let's look at this graph. Well, in this graph, I can't draw, but I think for this, I can just say in words. You can check that every vertex in the middle needs capacity like n. Because basically, if you draw any cut in the graph, then the neighborhood is just a single vertex, right? If you imagine fixing like any prefix of the path, then that whole prefix is adjacent to only the single next vertex. So that single next vertex is going to have really high capacity to accommodate the whole prefix. So basically, all of these vertices in the middle are going to need to have really high capacity. And in fact, they'll need capacity like close to n, or like n over log n. Okay, let's look at these 2 graphs. So the expander, the bottom left, there everyone just needs capacity 1. It's already an expander, you don't need capacities. And in particular, note that if everyone has capacity 1, this is just a normal definition of expansion. And finally, the bottom left graph, the 2 middle vertices, they're going to need capacity n. Because again, if you set your set L to be just like the left dongle, then the neighborhood of L is just the single vertex in the right dongle. And so that single vertex is going to need to have capacity n to accommodate for that whole left part. But if you look at other vertices, they have much lower criticality. So here, basically, yes, some vertices are very critical and you'll need to set kappa to be n, but for most of the vertices, you can set kappa to be around 1. Okay, so this is somehow one of the key definitions. Definitely stop me if there are questions about this definition or what it's doing. So we have this definition of capacited expander. And I want to point out that you can always find a function kappa that makes the graph a capacited expander. You could just set the capacity of every vertex to be n, and then it's pretty clear that it satisfies the definition. But our goal is, given a graph G, you want to compute a capacity function that makes G an expander, but where the total capacity is small. So why do we want the total capacity to be small? Well, because as we said, vertices with low capacity are not crucial. So if you start deleting edges around those vertices, you don't really have to do anything. It doesn't have a big impact on the expander. Only vertices with high capacity are hard to process. So as long as you have few vertices with high capacity, you're only going to have a small number of updates that are going to be hard to process. Great. Okay. So let me define a bit more. So why we want small total capacity, which is that basically I showed this technique of expander pruning, and it turns out we can very seamlessly extend that to work for capacitated graphs. So for this slide, assume that all vertices in G have constant degree, just for simplicity. And now you can define the capacity of an edge to be just the sum of the capacities of its endpoints. And so note that the total edge capacity and the total vertex capacity are basically the same because you have constant degree. So the statement is this. Let's say you have a graph G, which isn't necessarily an expander, but it's an expander with respect to capacity function K. And now the statement is the same as before, basically, that as you delete edges, the algorithm can always maintain a large expander inside G. So you delete some edges, so G might no longer be an expander, but some set X in G remains an expander. But now in regular pruning, the claim was that as long as you delete not too many edges, this expander remains big. That's no longer going to work here, because if you delete, for example, even just a single edge that has a really high capacity, we know that that can totally destroy the graph, and pruning will have to terminate. But the claim is that as long as the total capacity of the edges you delete is small, then again, your expander will remain big. So basically, you're robust to low capacity deletions, but you're not robust to high capacity deletions. So if we could make sure that most of our edges have low capacity, then we're going to be in a good spot. And that is exactly, so the key lemma is this. Basically, if you have any low diameter graph, then you can find a capacity function such that you have a capacity expander and the total sum of the capacities is small. It basically is directly proportional to the diameter, and you can show that this is tight, as it really needs to be directly proportional to the diameter of the graph. So this is the key lemma. In fact, we prove a very slightly stronger version of it that we need, but this really captures the key lemma. And this statement is true as given. The only issue with this statement is that, yes, such a function kappa exists, but we don't know how to compute it in almost linear time. So in the paper, we actually compute a slightly weaker function that only guarantees expansion for balanced cuts. You don't have to worry about this. But the above existence claim above really is true as stated. Okay, so we now have all the ingredients for a new robust core algorithm. Cyan, how much time do I have left?
I think
you can take.
Yeah,
so,
go
sorry.
ahead, Ramanujan.
So if you wrap up another 5 minutes, Aaron, that'll be great.
Okay, I will do my best. It might be 7. I will try 5.
Sounds good.
Okay, so basically here's the algorithm, which is that you start with your low diameter graph. You want to maintain a low diameter set. And it's really exactly the same algorithm we had before, except now, since your graph originally isn't an expander, first you compute a capacity function to make it an expander. Now you prune. So you maintain an expander inside G. And you maintain a ball around that expander, and you kick out any vertex that leaves that ball. This is exactly what we saw before. And much like before, if X becomes small, if your expander becomes small, then you have to restart from scratch, because you can no longer guarantee that if a vertex is far from the expander, that it's far from the rest of the graph. So this is exactly what we had before. So what we do if the expander becomes small is, okay, so you have your low diameter set K, but at some point you're no longer able to maintain K. So like you're sort of like, okay, I have my low diameter set, but I can't go any further. So then you just restart from scratch. You take your low diameter set K and you kind of recurse on that set, meaning you compute a new capacity function for the set K, you prune again, so you just like redo everything from your new low diameter set. So what is the analysis? Well, just like with random source, one phase is easy. All you need to do is compute this capacity function, which we can do quickly, prune, which we can do quickly, maintain a ball up to low diameter, which we can do quickly. The problem is that each phase is going to terminate after the adversary deletes n over log n capacity. But that's right, the adversary needs to delete that much capacity for the phase to terminate, because we said that our expander X is going to be large as long as the total deleted capacity is small. But recall that our key lemma tells us that the total capacity is only around like n. And so you can just see that the number of phases is at most 1 divided by the other, which is like a small number. So technically speaking, it's a little bit weird to say that the total capacity is only n, because every time we restart the phase, we compute a new capacity function. So to make this argument really work, we need to argue that this capacity function is monotonic between phases, which intuitively makes sense, because as you delete edges, things are vertices only get more crucial, so your capacities only increase. Okay, so that's the whole algorithm. The takeaway is that we have this key lemma, which basically allows us to treat any low diameter graph as though it's an expander and apply these really powerful expander tools without having to do anything like decompose the graph into expanders. So in terms of proving this key lemma, I don't have much time. So I will say the algorithm is basically the most trivial algorithm you can imagine. It's a constructive algorithm for kappa to prove that there exists this kappa with low total capacity. All you do is you start with kappa v equals 1 for every vertex. So if the graph is an expander, then this will already be enough. And now you just basically, as long as there exists a bad set, meaning there exists a set L such that its neighborhood has too small capacity, well, then you need to increase the capacity of that neighborhood. I'm sorry, I don't have time to draw a figure here, but basically, if you find the sparse cut, then you need to reinforce that cut. So you have to take every vertex in the neighborhood. Currently, their capacities are too small to accommodate L, so you just double their capacities. That's the whole algorithm. You find the bad cut, and you reinforce it by doubling capacities, and you just keep doing this. And it's clear that eventually your capacities will get big enough that you won't have any sparse cuts. The hard part is showing that if you just do this very simple thing, your total capacity will be low. And so that's a quite involved proof that I won't show. It generalizes, it like significantly expands upon an earlier technique of ours called congestion balancing. Basically, we define a potential function where you have a graph with costs where the costs increase with capacities, and your potential function is the cost of the min cost embedding of an expander into G. And you basically can show that this potential function increases monotonically and is tethered to the sum of capacities. So basically, whenever your algorithm increases capacities, that's also going to increase the costs in the graph, in this potential function graph. And we can show that because the costs increase, the cost of the min cost embedding also increased by the same amount as the capacities increase. And so these two things are totally tethered to each other. So since the potential function is small, the sum of capacities is also small. That's the full detail I will go into. Okay, so that basically covers it. So to quickly review, we solved this problem robust core, which basically said that given a set G of low diameter, you can maintain a set K inside it that has a low diameter and kick out the vertices that are far from the rest of the graph. And this is basically a subroutine that almost every previous algorithm for this problem had to solve some version of this subroutine. And this was a big building block for the adaptive algorithms. And so we show an efficient solution. And our key tool was this combination that you could basically turn any graph into a capacitated expander and then use expander tools. So to quickly summarize the results themselves, for shortest paths, there was a fast non-adaptive algorithm, but the adaptive algorithms were slow, and we bridged the gap and get a fast adaptive algorithm and basically settle this problem. For max flow, there was a fast algorithm. For approximate max flow, there was a fast algorithm only for the edge capacitated case, and we show how to extend it to vertex capacities or to costs. So we kind of solve the whole gamut, and we basically settle the picture for approximate flow and undirected graphs. And there were two things that were needed here. And the first is we need a new version of multiplicative weights to overcome the flow decomposition barrier. And then once we have that, we also need a fast data structure. So we just plug in our decremental SSSP data structure into our new MWU framework, and that's how we get our min-cost flow algorithm. Okay, those are all the results. Quickly finish up with some open problems. So I said we basically settle the problem of decremental SSSP in undirected graphs. For directed graphs, it's very hard from settled. We don't know, even our non-adaptive algorithms are pretty slow, and our adaptive algorithms are very slow. So we really don't know how to solve this problem. More generally, there are so many dynamic problems where there's this big gap between adaptive and non-adaptive algorithms. And I think closing this gap for various problems and developing general new techniques for closing this gap is a really interesting direction in the field. And finally, there are several algorithms now that use a fast dynamic data structures to speed up static algorithms. So for example, there's one that uses dynamic minimum cut to speed up the computation of a traveling salesman tour. But there are still not very many algorithms like this. And I think it would be interesting to explore more of the connection using dynamic algorithms as fast data structures. All right, that's the talk. Thank you all so much for coming, and sorry again for the technical issues.
Thanks a lot, Arun, for the nice talk. So I'm applauding on behalf of everyone. There you go. Thanks again for the nice talk. So are there any questions for Arun?
Can I ask one question?
Sure.
So there is this n to the power little o of 1 subpolynomial time in your factor hidden in your total update time.
Yes.
How difficult do you think it will be to remove that to get some truly m times polylog update time algorithm? Will it be just some minor technical issue, or will it require significantly new ideas to get rid of this term?
I think it would be incredibly difficult. So I know it seems like the difference between n to the little of 1 and polylog is just like some technical tweak, but it's a big open problem. And in fact, the non-adaptive algorithm also has an n to the little of 1. So this actually has nothing to do with robust core. That n to the little of 1 does not come from robust core. It might also come from robust core, but that's not the main place it comes from. The main place it comes from is that all of these algorithms, including ours, right? I said that once you compute robust core, how do you use that to compute shortest paths? Well, you sort of maintain these low diameter balls and you compress them. So what you're actually doing is you're constructing something called a hop set.
Okay, I see.
And so our algorithm also constructs a hop set. It's like the building block is different, but in the end, we're using the same general framework, which is you construct a hop set. And there are lower bounds showing any hop set. No matter what you do, the hop set will involve an n to the little of 1 factor.
Yeah, so just to clarify, do I understand it correctly that the hop set lower bounds are unconditional? They are just
they're totally unconditional. Yeah, they're just like you just show a graph where no good hop set exists. Yeah.
I see.
So thanks again, Arun, for this very nice talk.
Yeah, thanks again for inviting me.
Thank you all for joining.